Hi folks, Mr. Ackerman here. Thanks for watching. Topic of today's video is elastic potential energy and simple harmonic motion. And this is a fairly new topic for grade 12s. I know you've talked about elastic potential energy in the past. You've talked about the potential energy stored in a spring that perhaps is stretched, but you've never actually looked at the details of this elastic potential energy or the forces that have to be applied to stretch the spring in the first place. And that's what we're going to be doing that's new in grade 12. So in a moment I'm going to ask you to pause the video so that you can have a look at what questions we're going to answer, as well as where we are in the homework schedule, the unit schedule rather, and also what are the learning goals and success criteria. So please take a moment to pause the video and have a look at the screen. Okay, great, and you're back and we're going to dive right into this. So let's take a look at our first slide. First of all, I want you to take a look at these two pictures here. You see, one of them looks kind of like maybe a character from Game of Thrones. This is an archer, and he seems to be pulling back on a bow. He's trying to shoot an arrow. If you've ever done archery before, or maybe just by watching you can tell, there's a sort of elasticity to the bow, and in fact, as you pull back, it gets harder and harder, and if you can manage to pull very far back, you can shoot the arrow with a greater and greater speed. Of course, this has something to do with the forces that are exerted on the arrow when you release it. And of course, the arrow will begin moving. There'll be kinetic energy. So right away, we know there's something dealing with forces, elasticity, energy. That's what we're going to start talking about. But to simplify matters, I'd like you to take a look at the second picture. Just imagine a spring. Perhaps it is up against a wall. Let me put in a little wall here. Maybe this is the wall in the classroom, and here we are sitting on a lab bench with this spring. You're going to do a similar lab in class, not quite the same, but what I'm going to ask you to do is to somehow in class begin applying forces. So let's draw a force vector perhaps in this direction like this. Imagine if you could apply a force that we're going to call FA for applied. What would end up happening? Well, of course, the spring would stretch. Initially, it probably wouldn't be stretched, so we could call its starting position x equals 0. This would be the unstretched position, and of course, as you applied more force, it would stretch more and more. You might even plot a graph of the applied force, Fa, measured in newtons, as a function of the amount of stretch. The idea being here that more stretching leads or requires more force. Now, if you did this, you would probably find either a straight line going up, like this. Would it be linear? Perhaps. Would it be some sort of a curve going this way? Perhaps. Would it be some sort of a curve going that way? Perhaps. I guess we'll have to do a lab to find out, and if you look in the unit schedule, you'll see there is a lab that we're going to do on this. What you're going to find in the lab that we're going to do is that you end up with this shape right here, a straight line. And this is the case for springs that we call ideal springs. An ideal spring is one where the amount of stretch is proportional to the amount of force applied. Of course, no force leads to no stretch, so the origin is one point here. So it's a straight line through the origin, and this, of course, has the general form of y equals mx, if you think of math class. The vertical variable equals a constant, the slope, times the x variable, which in math class is x, and in this case, for x, the number of meters of stretch is also denoted by x. So let's just replace all the letters that we have in this diagram. The applied force equals, now for slope, on this kind of graph, physicists like to use the letter k, so we'll have to put that in. K is the slope here, it's a constant, so k, and they keep the letter x. And basically you've discovered the law, if you will, of ideal springs, that the force that you need to apply is equal to some constant times the amount of stretch that you want. Now the constant being the slope is going to have units of rise divided by run, and if you look at your rise, that's in newtons, and if you look at your run, that's in meters. So the slope, the k value, actually has units of newtons per meter, and this is called the spring constant. I'll leave it to you to take a look at this graph and satisfy yourself that if you have a larger K value, it requires more newtons to get each meter of stretch. And so we have a name for springs that have large K values. Since they require so much force to stretch them, the higher the K value, the more stiff we say the spring is, or the harder the spring is. And if the K value is smaller, indicating fewer newtons required to stretch each meter, then we call that a softer spring or a less stiff spring. But anyway, getting back to the graph here, like I said, you're going to, quote, discover this straight line relationship in class. And another word for this kind of spring, the ideal spring, we also call it a Hooke's law spring, named after Robert Hooke, to whom this law obviously is attributed. Hooke's law just tells us about the force needed to stretch this kind of ideal spring. The interesting thing that you have to keep in mind, however, is the following. If you pull a spring to the right, the spring will pull back on you to the left. This is just Newton's third law, the law of action and reaction. So allow me for a moment to indicate the following. A force going in the opposite direction, I'll use a different color because this is the force exerted by the spring on you. And so this would be not the applied force that you are applying, but the force that the spring is applying back. So we're going to call it Fx because we want to denote that the spring pulls back on you harder if you pull on it harder. And as we just saw from here, the hardness, or rather the force of that pulling, is related to x. So this is what the spring returns on you, and it's in the opposite direction as your displacement. So Fx in the opposite direction is negative kx. You'll see this formula actually written as Hooke's law. So even though I wrote Hooke's law as being this, it's not so much that, it's more this. Hooke's law tells us about the force exerted by the spring, but often we kind of talk about the two interchangeably, so I just want you to be aware of what's going on there. One other interesting thing to point out here is you don't have to stretch the spring, you could always compress it. This spring looks like it's got some space between the coils. Why not compress it? Why not apply a force on the spring this way? Fa now to the left. This is your applied force. What is the spring going to do? Imagine compressing a spring. It'll want to decompress. So it will push back on you. I'll use a different color here, maybe orange. The spring will now apply a force on you. We'll call this Fx, again in the opposite direction. And so the formula with its negative sign does indeed work out. All right? In a moment, we're going to take a look at one of the sample problems in the textbook that deals with this. I know you see some space at the bottom here. I want you to hold on a sec. I needed this space because I've run out of screens, and I'll need to use this later. So just hold on. We're not quite here yet. What we're going to do now is jump to a question here. And the question deals with a ball which is going to be hung from a vertical spring. And what do we mean by a vertical spring? Well, imagine a spring that is hanging from the ceiling, okay? The ceiling in the physics classroom, for example. And what you're going to do is attach a ball to that spring, and of course gravity is going to pull that ball down, and so the spring is going to stretch slowly. And by the way, before I forget, this question is taken from the textbook Physics 12 by Nelson, just to give credit where credit is due. Anyway, getting back, we have a vertically mounted spring, so let me start drawing this. Here's the ceiling, and here we often show that with these little tick marks here. So we have a spring which is hanging, and we're going to attach a ball of a certain mass, like this. 0.075 kilograms is its mass. Now, this is important here. The mass is allowed to stretch slowly, it says, from its unstretched position, that would be x equals 0, all the way down a certain distance to what is called a new equilibrium position, 0.15 meters below the initial one. So let me just draw this in. Let's draw this mass a little bit below where it started. Maybe down here. And now let's think for a minute. If you allow something to slowly fall, that means you can't just let go of the mass. If you let go, it's going to start falling and bouncing up and down like this. So you got to take your hand and slowly lower it until it kind of settles into a place where it's in equilibrium. Okay, why is it in equilibrium? Equilibrium is a word that reminds us of forces, and sure enough, forces are acting here. What are the forces? There is gravity acting down, so we're going to put Fg equals mg. And there is another force acting up. What is that force? Well, thinking back to this slide over here, it's the reaction force of the spring in response to being stretched, this time by gravity. So I'm going to put an upward force. And because we've used our hands to just carefully steady it, this will be Fx equaling negative kx. What direction is the positive x direction? It is, of course, straight down. This distance here is the 0.15 meters that they told us about in the question. Remember, positive going down, therefore the negative here will tell me that the force is pointing up. And they ask, first, what is the force constant? They call it the force constant. Sometimes it's called the spring constant, which is what I did. So let's have a look here. In part A, we've got forces in equilibrium. So what can we write here? We can write that F net equals 0. That's what equilibrium means. And if we've got F net equals 0, and we know what F net is made of, it's a positive mg pointing down, and a negative kx pointing up. Well, let's see. They give us the mass, they give us g, they give us the x value, the amount of stretch, and they ask us to solve for k. So I'm going to leave it to you to now solve for the k value. Of course, you can follow along in the textbook solution. They do it as well. Let's take a look at question B now. They say you now return the ball to the unstretched, so this means x equals 0, equilibrium position. So you hold it back up in this position right over here. But now you allow the ball to fall. You remove your hand and just let it start falling. What's it going to do? Well, it's going to pick up some speed and it's going to start bouncing up and down like this. What they're asking now is, what is the net force when the ball has dropped this amount, 0.071 meters? Now let's think critically for a second. If you allow the ball to fall this time only 0.071 meters, that is less than what it was in part A. So the ball will not have fallen as far down in the time or at the point where we're solving this question. So that means Fx won't be as great as it was in part A. The forces won't be balanced. This is not an F net equals 0 question. This is a new question. Let's draw it in over here. I'll try to draw the diagram in line so that you can see with the other diagrams. Okay, here we go. I want to show that this time the mass is somewhere in between where it started. Here's where it started. This was the x equals 0 position. And here is the new position right along here. You can see it's not as far as in the previous question. It's only about half as far. And they ask you, what is the net force? Well, first of all, can we say that gravity is still the same? Sure we can. The reason we can say that is because the mass has not changed. So I'm going to just cut and paste and put that back there. That's the same. However, the Hooke's law force is now going to be a little bit less than it was in part A of the question. So I'm going to draw this a little bit shorter. Fx equals negative kx. Of course, you know what x is. You know what k is, because that's what you're supposed to solve for in part A. So use your answer from part A to sub in for the k value. Use the x value here, You know what mg is from part A. Find me the net force. What's the net force here? Well, same as up here. F net equals, we have positive mg, and kind of running out of space there, minus kx. You can solve for F net. And then you can easily do part C, which asks for the acceleration. Whoops, sorry, that wasn't a very straight line. Asks for the acceleration of the ball. How do you find acceleration? Well, if you know F net, and you know Newton's second law, you know the acceleration. Use your answer from part B to sub in for F net. You already know the mass, and so now solve for A. And that's how you do this question. This is a question involving forces only and accelerations. All right? Now I'm going to jump back to this screen here, which I told you hold on a sec a moment ago because I would like to address this. We've talked a lot about forces. Now if you're applying force to stretch a spring, then that means you have the ingredients, force and distance. You're stretching a spring a certain distance. You have the ingredients for work. Of course, you also know intuitively if you stretch a spring, then you are storing elastic potential energy in it because you can always release that spring and let it snap back, and then suddenly it's going to be moving with kinetic energy. Where did that energy come from? It was stored as potential energy. How do we find the work done? Well, you might think, and this would be a natural thought, it'll be F delta D cos theta. You go to this spring here that we talked about earlier, you apply a force, and it stretches a certain distance x. It stretches out this way. The force and the displacement are in the same direction, so you have cosine of 0 degrees. The force we just learned is kx. The distance that you stretch it is x. Cosine 0 because it's stretching in the direction that you're pulling. What do you get? Kx squared, right? Yeah, it's right. But the formula does not give you the work. This is wrong. Why? Pause the video for a moment and see if you can detect the flaw in my logic here. Okay, and you're back. Maybe you figured it out. Maybe you didn't. I'll give you a hint. Look at the Game of Thrones guy over here. This guy's pulling on a bow, which is exhibiting characteristics of a spring. The more you pull it, the more energy you store, the more force you have to apply. But think for a moment. When he begins pulling, like at the beginning, pulling is really easy. By the end of the pulling, over in here, pulling is really tough. It requires a lot more force. So the force is not constant. That is because the x value is changing throughout the pulling. So you can't use a formula for constant force. That's what this formula is for. It's for constant force. You can't use that to get a formula for the work done. So what are we going to do? Well, I'll remind you that we have a graph from above. It's gotten a little messy, so I'll just reproduce it down here, and you can take a look. This was the force versus stretch graph. What do you know about work and this kind of graph? If you guessed that the area beneath the graph is equal to the work done, then that's good. You've remembered something from the beginning of this unit. The area beneath a force displacement graph is work done. And this is a triangular area, so that's going to be a half base times height. Now here's one more hint. The slope is equal to k, so I'll tell you what. Here's the base, which is clearly x, but what is the height? And then once you figure out that in relation to the slope, I bet you'll be able to derive the formula for the work done when you actually stretch a spring. It is a half kx squared. So we were kind of close before. We thought kx squared, but actually it's a half kx squared. This is the formula that we want, And this, by the way, is the fact of the day. And the reason I made this the fact of the day is I don't want you to ever think that the work done is a simple F cos theta delta D when the force is variable. Here the force is changing. You got to use a different method. This one works. And by the way, we have another name for the work done. Since you're doing work on the spring, you are storing energy in it. We also call this the elastic potential energy, or E with the subscript E. All right. Now in a moment we're going to see how to use this formula, but first I'd like to show you an interesting system of a mass on the end of a spring. The spring is mounted horizontally to a wall, kind of like I described to you earlier. And what we're going to do here is try to imagine taking this mass and stretching it out like you see in figure B here, and then letting go so that the spring naturally pulls the mass back and the mass begins moving. Of course, the mass is going to overshoot the original x equals 0 position, and it's going to compress the spring like you see in figure D. And of course, once the spring gets compressed, it will push in the opposite direction, and it will cause the mass to go to the right. And if there's no friction, which I've mentioned up here, then what's going to happen is this mass will just keep going back and forth all day. In fact, I found a nice little simulation for you online that you can take a look at. It's right here. You can go to this website, physics-chemistry-interactive-flash-animation.com, and what you'll find is this. You can take this, click and drag this mass, which is mounted on 2 springs, as the case may be, and release it. And it vibrates back and forth. There's a motion sensor over here, which is designed to measure the motion of the spring. And if you click Start up here, look what you get. You get a graph that shows how the force keeps changing, going positive and negative, because the force is changing direction. And the position is oscillating back and forth, not going negative, because in this position graph, the starting position was not at 0 at the motion sensor, it was a little distance away. So watch what's happening. As the position changes, so does the force, but you'll see they're going in opposite phase to one another. When the position goes close to the motion sensor, the force points one direction. When the position goes far from the motion sensor, the force goes in the opposite direction. So the force is oscillating opposite phase to the motion. All right? You can stop this and investigate the graph, or you can go play with it on your own, but that's a good example of what's going on. Back to the analysis here. We have a name for this kind of motion. It's called simple harmonic motion, and it has some very interesting applications that we'll get to shortly. However, what I'd like you to do is first think about what we mean by simple harmonic motion. Harmonic as in repeating back and forth on a regular basis, but also something very interesting. Because there's no friction here, if you think about it, when you pull this mass the first time, you apply a force that has to be equal to the force that the spring is pulling on you. So you apply force kx, the spring pulls back with force negative kx. Suppose the amount you pull is equal to the letter A, which is meant to represent the maximum amplitude of the vibration. Now, because the force is proportional to the stretch distance, x, which in this case is equal to A, therefore, as the spring returns to its normal position, the force becomes less and less, and the acceleration becomes less and less. Eventually, the mass gets back to where it started, which would be right around here, and now there would be no stretch or compression, therefore no force, no acceleration. But then the mass will overshoot that position, as we saw a moment ago in the demo or in the simulation, and now the force will begin building again. In fact, the greater the compression, x, the greater the force. This is a situation where the force kind of depends, or not kind of, but does depend on x. And because the force is related to acceleration, as we saw in an earlier problem, therefore the acceleration depends on x. That's what simple harmonic motion is. It's a type of motion where the acceleration is proportional to the distance from the equilibrium position, and you end up with this back and forth kind of motion, which we're going to see a lot of in the next few minutes. If you wanted to do a calculation involving simple harmonic motion, one thing that you would obviously want to know is, what is the period of the vibration? Remember from grade 11, period is the letter T, T as in time. So the period in seconds for the vibration is given by the following formula. I'm not going to derive this for you. It's in your textbook and you can look it up if you want, but to save time I'm just going to tell it to you. It's 2 pi times the square root of the mass of the object divided by the k value of the spring. If you think about this logically, how should changes in mass and spring constant affect the period? Pause the video and think for a moment. If we were dealing with a very, very heavy and or very, very stiff spring, what would that do to the period of vibration? Pause the video and think about that for a sec. Okay, and you're back. Now let's think. If you have a really, really heavy mass, should it take more time or less time for the mass to vibrate or oscillate back and forth? I think it makes sense that if you have more mass, it should take longer for that spring to pull the mass back and forth in simple harmonic motion. So it makes sense that m is in the numerator. And what about the reverse? Or that rather, what about looking at k, the spring constant? What if you had a really, really, really stiff, strong spring? Then that spring would be able to snap that mass back so quickly that it would oscillate back and forth at with a very low period. So by increasing the k value, being in the denominator, you decrease the period, and therefore it takes less time to go through a cycle. The period formula at least makes sense in some way. Where did the 2 pi and the root come from? Check your textbook to find out. And while we're at it, frequency, which is just the reciprocal of the period, remember, 1 over t, that'll just have the reciprocal of all these, so 1 over 2 pi and root of k over m. So there's some formulas for you. Now, getting back to this one more time, let's talk a little bit about the energy that's involved here. When we start out, the spring is not stretched. X is 0. So there's really no energy to speak of at all. There's no stored energy. There's no kinetic energy. Now we stretch the spring. So in this diagram, diagram B, we haven't let go yet, but we have stored a lot of elastic potential energy. It's a half kx squared. And if we know that we're stretching a distance a, we will know that we can sub in whatever value a has, and that'll give us the elastic energy. Of course, the mass is not yet moving, so E kinetic is equal to 0. And so we could actually calculate something called E total. Since we're dealing with elastic energy and kinetic energy, and we're going to have a value for EE, and we've got 0 for EK, can add those up and get E total. Now a moment later we release the mass and it begins moving. It immediately picks up, it gains some EK. But where does this EK come from? It can't come from nowhere. That's what the law of conservation of energy tells us. Don't forget that. Well, where does that energy come from? If we're gaining EK, it must be at the expense of EE. So we lose EE. And does that make sense? Sure it does. The spring is becoming more and more unstretched. It's getting back to the equilibrium position. If you were to now calculate EE at a half kx squared, k would now be less than, that's the less than sign, a, so the value would diminish from what it was in diagram B. Of course, if you were to add up the total values of energy, you'd have a new EE that was a little bit less. So you know what I'll do? I'll draw that EE a little bit smaller. How about like that? A little bit smaller than before. And I'll draw EK a little bit larger, just to signify that this one's diminishing, that one's increasing, but their total is the same as whatever number of joules you had before. and the process continues. We have an energy transformation going on here. It's governed by the law of conservation of energy. And at this point, I'd like to have you take a look at an even more challenging example involving energy transformations. So we're going to go somewhere that we've been before. It's the PhET website, where they have some simulations. And the one I want you to click on and download, it won't harm your computer, don't worry, is under Physics, under Work and Energy and Power. It's called Masses and Springs. So you're going to download that, and what you're going to get is this fun little toy to play with. You've got a ruler that you can move around. You've got a little line here where you can designate the starting point, and you can line up your ruler if you want. You've got some masses down here that you can click onto a spring, and you can just let it kind of hover there. I think you can even pull this and let go and watch what happens. There's that vertical oscillating spring again. In fact, if you want, you can go back to one of the questions that maybe this didn't make so much sense earlier. Well, I bet you now it's going to make a little bit more sense if you play with the simulation. Now, if you want to get rid of this, you just have to grab it and pull it off of the spring, and then it makes that noise. I don't know if you heard that, but if you've got the sound turned on, you'll be hearing this when you download it. I like to play with spring number 3 because spring number 3 gives me some controls that I don't have with spring number 1 and 2. For example, let's add a really heavy mass. Let's give it a little pull here, and let's let it oscillate. Now here's what I can do with this simulation. If I want to watch things move in real time, I click real time here. That's a little fast sometimes, so I'm going to slow it down to 1/4 of the speed. I can go and make sure I'm on Earth, so watch this. Instead of making g = 0, let's go into Earth gravity. Whoa, okay, all of a sudden that mass started moving, so now I've got to try to grab this and take it off. There we go. Okay, we're back on Earth. You can go to the moon, Jupiter. It's a lot of fun, so you should definitely play with this. Let's take 100 grams maybe, connect that, and just let go of it very carefully. You can see it already vibrates up and down quite a bit. You can show the energy of this spring over here. Look at what's happening here. The spring is moving, so it's got kinetic energy shown in green. It's going and stretching the spring, so there's elastic potential energy. They call that P-E elastic, potential energy elastic. It's also moving up and down. If you look back at what we had over here, the spring was only going sideways. There was no change in gravitational potential energy, but this one does have that, so it's a little bit more complicated. However, if you watch how these graphs are moving, you'll notice that the total energy always stays constant. It may be a mixture of green, which is kinetic, dark blue, which is gravitational, and light blue, which is elastic. However, it always adds up to the same amount. When the mass is moving a lot, there's kinetic energy. When the mass stops, the kinetic energy goes to 0, like now and now. The gravitational energy increases when the mass goes up and decreases when the mass goes down. And the elastic energy increases when the spring stretches and decreases when the spring unstretches. Now here's where you can have some fun too. You can change the softness, this is the K value of the spring. Let's make the spring less hard, a softer spring. And now look what happens. Now the same force pulling down really stretches that spring. On the other hand, if you increase the K value, now the spring barely stretches, but it whips back and forth at a much higher rate. Memories of this formula down here? I think so. Play around with it and get an idea. Another thing you can do is add friction. What do you think would happen if I added some friction here? Would the mass keep going forever and ever? Let's watch. Now you see the thermal energy building up. It's building up in its own sense, and it's building up as a percentage relative to the total energy. Watch what's happening to the motion. It is actually slowing down, getting less and less kinetic energy, less and less of all the other kinds of energy, and sure enough, very shortly, this mass will come to rest. All right, so a lot of fun that you can have with this, and we're going to need to keep these ideas in mind as we go on to our final, or second last, slide. This is also out of your textbook. It's sample problem 3 in the book Physics 12 by Nelson. this time we've got elastic potential energy involved. We're going to use the half kx squared formula. So there's an apple which is attached to a vertical spring, force constant 9.6 newtons per meter. The apple is held so that it is on the spring at the unstretched equilibrium position, and then it is just allowed to fall. It's let go of. So go back to the PhET simulation and see if you can do that. Take one of these masses, attach it to a spring, and just let go of it and allow it to fall, as opposed to slowly lowering it. What do you think is going to happen? Well, the mass is clearly going to fall down, it's going to get pulled back up, it's going to bounce up and down like this. So first of all, let's get an idea of what's going on by drawing a quick diagram. Here will be our ceiling, and I'm going to draw some tick marks here to designate that. They ask us to figure out if you take the apple and attach it to the spring when we're at the unstretched equilibrium position. So let's call this the unstretched equilibrium position. This will be x equals 0. And now you let go so that the mass begins falling and the spring stretches, and now you end up 11 centimeters below where you started, 0.11 meters, and this will be positive x going this way. What is the elastic potential energy stored in the spring? Well, that's easy. EE is a half kx squared. So all you got to do is sub in your k value and your x value. Make sure you're in meters, by the way. This shouldn't be a problem. You're going to get a certain number of joules of energy when we're down here. Now, what is the mass doing at this point? Well, it's either still moving or it has reached its maximum stretch and is about to pop back up. Do they tell us which one it is? They don't. And in fact, I think it's safe to assume, or at least we should start by assuming, that this is not the lowest position. Perhaps the mass can actually fall more. How would we ever know if that was the case? Well, maybe if we look at the energies that are involved. For example, what kinds of energy do we have here? We definitely have E elastic, and we've got motion, so there's E kinetic. There's also vertical changes, so this will be EG. And if we use the idea that each of these added up gives us E total at any given time, then what we might do is compare E total initial with E total final. For example, what would we have here for EE? There's been no stretching, so EE is 0. And for that matter, we haven't allowed the mass to move, so E kinetic is 0. We are, however, a certain distance above the lowest point, so if we set this as height equals 0, we can do mgh and figure out the total value. We can add these all up and get our E total value, E total initial. Now let's look at what's going on here. The spring is stretched, it has elastic potential energy, and in fact, that is what you solved for in part A. The spring, the mass is at the lowest point, so its EG is equal to 0 now. And the question is, does it have EK? Well, maybe it does, maybe it doesn't. I'm betting that it does, because it would be highly unlikely that this very number that they gave you is the lowest point. It could just be a random point, but regardless, EK is a half mv squared. You're supposed to be able to add these up to get a number called E total, this time final, and that value is supposed to be equal to this value over here because of something called the law of conservation of energy. And folks, I think if you apply this idea, you ought to be able to solve for the speed. If it turns out to be 0, then I guess this was the lowest point in the question, the lowest point that the mass can go to. But if it's not 0, then I will have been right, in which case the mass was still moving when it fell down this far. All right, this is a question involving energy ideas as opposed to the previous one that dealt with acceleration and force ideas. All right, we're going to wrap up with a quick talk about some applications of these springs and elastic potential energy. One that is of supreme importance is the relationship between springs and timekeeping. Because of the fact that the spring force acts opposite the displacement, there's that sort of restoring force and the ability of springy things to oscillate back and forth. In fact, that's exactly what you need to have accurate timekeeping devices. If you had a reliable ideal spring that could always be counted upon to snap back to where it was before you deformed it or displaced it, then you could build yourself a wristwatch, for example. What would society be like if there was no accurate timekeeping? How would we be able to stay on schedule? How would we be able to know the universe? After all, so many things depend on time. For example, speed depends on being able to measure time. So does acceleration. And acceleration is related to forces. How could we understand forces if we didn't understand time? Well, I don't think I need to get into a whole big discussion here about how important timekeeping is. And once you understand that, you'll understand all these little gears and whatnot and the movements in these watches. This is a see-through wristwatch. All of those are ultimately based on the ticking, which comes, of course, from springs. And then one more. We talked about something macroscopic, a watch. Let's talk about something microscopic. You learned way back in grade 9 that molecules are in constant motion. They translate, they move from one place to another. They rotate, and they also vibrate. Well, as you get into grade 12 chem and beyond, I'm sure you'll talk about these vibrational modes and the energies that are associated. Here's a page, this is from Wikipedia, and I'm going to take you to that page in a moment. By the way, just to give credit where credit is due, this one is off of Google Images, a Google image search. It's not my watch. So anyway, Wikipedia, the title of the article is Molecular Vibration. You can see there's several different ways that a molecule can vibrate, and these energies and these vibrational modes, as it turns out, can be described by assuming simple harmonic motion is what's going on. So here's the page. You should definitely check it out. It's very interesting, even though I don't understand all of it. I'm not really a chemist. I can understand enough of it with a grade 12 physics background and also the chemistry background that I know, and maybe doing a little bit of extra research. And that's it for now. That's the end of the video. I hope you've enjoyed. I hope you've learned a lot. Sorry that it took a little bit of time, but there were a lot of topics, and we will do some more investigation in class. All right, thanks for watching, folks, and I will see you later. Bye now.